gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at properties that we're going to use to describe our gases. Now there's 4 different variables that we'll use to define a state of a gas. The first one will actually be moles of gas. All right, I guess let me start that over here. So the first one will be moles, all right, normally abbreviated as an N. And moles of gas comes into play, and it's really just a way for us to quantify the amount of molecules present. All right, and so again, we're running back to stoichiometry, and we're thinking, all right, moles is a quantity, so if I have 5 moles of a gas versus 10 moles of a gas, I know that I'm being given a quantity there, and it's to describe the number of molecules that are present. All right, the second thing that we're going to use to describe a gas is actually the temperature of a gas. Now, normally when we're talking about temperature of a gas and we're trying to describe characteristics about the gas, we are going to be discussing temperature in Kelvin. Now, I understand that we have Fahrenheit, degrees Celsius, and then we also have Kelvin. We will rarely, if ever, use Fahrenheit. Anywhere in science, that's an American standard, all right? We will generally be dealing with either Celsius or Kelvin. And the way that we convert back and forth between them is really simple. Degrees Celsius plus 273 is equal to Kelvin. And that's one of the more important temperature conversions that you'll want to be familiar with, all right? Now, here's the big thing for temperature, all right? In Kelvin, temperature is directly proportional to the average kinetic energy of the molecules, all right? And that's really important that you get that down word for word. In Kelvin, temperature is directly proportional to the average kinetic energy of the molecules, and you've probably heard me say it before by now. That's where we get the term heat 'em up, speed 'em up, right? Because the higher Kelvin temperature means that I have a higher average kinetic energy, i.e. my molecules are moving faster, or more of them are moving faster. And so one thing that we will definitely want to make sure that we understand and we will use to describe the number of molecules and their average kinetic energy is called the Boltzmann Distribution, all right? Now, Boltzmann's distribution, if you're going to look, it's really just a graph, and on the y-axis, we've got number of molecules, and then on the x-axis, we've got the speed of the molecules. And in this particular graph, I'm going to go ahead and draw the first one here. We'll start out, and notice it's just like a bell curve, all right? With the top of the curve being the average kinetic energy of the molecules. So, for example, if this first one was 273 Kelvin, what would they look like if I heat them up, right? So that whole heat them up, speed them up. And so what we see, if I change colors here, is we'll actually see that the curves themselves will actually start to flatten out, right? And notice, but on top of the top of the curve is still my average kinetic energy, so let's say maybe this is 1273 Kelvin. Notice, again, it's just flattened out, and so I've got more molecules that are actually moving at a higher speed, and then again, if we increase it one more time, you'll see that we get this general flattening of this curve, and we'll say that maybe this is 2273 Kelvin. Now, I made those numbers up, and it's just to give you the general idea that we understand that the space underneath the curve, or the area underneath this curve, is representative of the number of molecules that are moving at any given particular speed. And we see that as we spread that curve out, I get a higher or a larger number of molecules that are moving at a higher speed, i.e. the average kinetic energy has shifted, right? And we can see that the top of the curve actually shifts over to the right. I get more molecules, I get that higher average kinetic energy. And again, it's really important to understand that this is all based on a Kelvin temperature, and that Boltzmann's distribution just graphically shows the effective temperature on the number of molecules with a given molecular speed. And so that's a good definition for Boltzmann's distribution. It just graphically shows the effective temperature on number of molecules with a given molecular speed. All right, and now my third variable is actually the volume of a gas, right? And volume, this is normally going to be reported in liters. Now, you can get milliliters, and we can just use our dimensional analysis to convert from one to the other. And essentially, another thing that we need to understand, that gases do take the shape of a container. So if I had a container, I'm not going to draw a bunch of gas molecules over here on the side, right? I wouldn't do that. I would have to show my gas molecules evenly distributed throughout the container. And that's a really big point to understand. The other thing that we really definitely want to get across is that the size of the container actually dictates the number of collisions that my molecules can have with the size of with the sides of the container, right? So the larger my container, the more space my molecules have to move in, the less collisions I would expect them to have with the side of the container. And that's going to become really important when we start trying to relate these variables one to the other. All right? The last one that we're going to take a look at is pressure. Now, pressure is really, really important. Now, pressure is defined, and it's really looked at as a measure of the force a gas exerts on its containers through collision in a given surface area. So again, a very important definition for pressure. It's a measure of the force a gas exerts on its container through collisions in a given surface area. So make sure that you understand collisions with the container, that's what pressure is, right? So the more molecules that I've got colliding with the container, the more pressure I've got, all right? The faster my molecules are moving and hitting the side of the container, the more pressure I've got. And so it's really, 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 and I didn't write that definition down that I gave a second ago. I hope you did, right? So more collisions equals a higher pressure. And that's something that we really, really, really want to get into our heads, right? Is that pressure, all I have to think about is, hey, am I going to get more collisions with the side of the container? If I do, I'm going to have a higher pressure. If I don't, then I'm going to get less collisions, then I've got a lower pressure. And then we're going to finish this out with my units of pressure, right? And pressure is normally abbreviated with that P, right? We've got ATM, which stands for atmospheres. We've got mmHg, which stands for millimeters of mercury. We've got torr, which are torrents. We've got PA, which are pascals. And we've got kPa, which is kilopascals. Now, the American version of PSI, which is pounds per square inch, we're not going to be dealing with that guy. And then to be honest with you, we generally won't deal with pascals, and we generally won't deal with torrents. And so the major pressures that we'll need to understand and be familiar with are really atmospheres, millimeter of mercury, and kilopascals. Now, the conversions between the two, I'm just going to give it as one long conversion here. 1 ATM is equal to 760 millimeters of mercury, and that's also equal to 101.3 kilopascals. And these are the conversion factors that we will use, ladies and gentlemen, to actually convert from one type of pressure to another. All right? Okay, that was a whole lot, ladies and gentlemen. If you have any questions, I hope you got them down. I'll see you in tutorials for those, and otherwise, I will see you in class.